We'll finish up the discussion today talking about something called Beats frequencies. A Beats frequency is the frequency of the amplitude fluctuations of a wave. Now, what you have is two waves that are very similar, but they have a different frequency, F1 and F2, and they also have a different wavelength. Now, when they're together, at some points they have destructive interference, and at some points they have constructive interference. And what you notice is that these occur in regular intervals. And this is what's known as a beat, or a Beats frequency. You hear this, and then it's followed by a period of silence, then it's followed by another construction, and it literally goes wah, 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 like that. And that's known as a beat frequency. And people use this in tuning instruments again, because when they're close, how often the beat frequency occurs tells you how much different the frequencies between these two waves are. Beats are produced by the superimposition of two waves that are of slightly different frequencies. The waves alternate in time between constructive and destructive interference, and this gives a result of a time-varying amplitude resulting wave. And this is what's known as the beat, and you can hear it when you're tuning a guitar or whatever. So let's take a look at a couple more problems. Two jet engines on an airplane are producing an average sound frequency of 4100 hertz with a beat frequency of 0.5 hertz. What are their individual? So their combined is equal to F1 plus F2 divided by 2. So FB is going to equal F1 minus F2. So F is equal to FB plus F2 divided by, or plus F1 divided by 2. And so that's going to be 4100 minus 0.250, which is equal to 4099.75, and the other one's going to be 4100.25. And what you notice here, if you take the beat frequency, divide it in half, and subtract 1 and add it 1, you end up with the two together, and that's the beat frequency. A wave traveling on a slinky that is stretched to 4 meters takes 2.4 seconds to travel the length of the slinky and back. So a total of 8 meters is 2.4 seconds. So it's asking, what is the velocity of the wave? Well, the v is going to be the distance divided by the time, or 8 divided by 2.4, which is going to equal 3.33 meters per second. The second question is, using the same slinky stretched the same length, a standing wave is created that consists of 3 antinodes and 4 nodes. So it's a second overtone. What is the frequency? What frequency must the slinky be oscillating? So V is equal to mu, or not mu, lambda f. This is a formula from a previous understanding that the velocity of a wave is equal to the wavelength times the frequency. And so this tells you that F is equal to V divided by mu, or lambda, excuse me. So 3.33, and it's stretched the same length, so the wavelength is 4. So the frequency is 1.25 hertz. And that that frequency. Now let's briefly talk about intensity. Intensity is the energy per unit time, or the power per unit area of a wavelength. So intensity is equal to power divided by area, or energy per unit time divided by area. Here you have stereo speakers producing both constructive and destructive interference in a room. This is a common to all superposition of waves. The shading is proportional to the intensity. Where you have constructive, you have greater intensity. Where you have destructive, you have lower intensity. And this is sound waves. So intensity is not only sound, but also light, etc. So let's look at a couple more problems. Suppose you have a device that extracts energy from the ocean breakers in direct proportion to their intensity. If the device produces 10 kilowatts of power on a day when the breakers are 1.2 meters high, how much will it produce when they are 0.6 meters high? The power is proportional to the energy, which is proportional to the intensity, which is proportional to the square of the amplitude. So power of 1 is equal to the amplitude squared, and therefore P2 is equal to P1 times x2 over x1 squared. So we got 10 times 0.6 over 1.2 squared is 2.5 kilowatts. So it reduces by a 1 over 2 squared, or 1/4. If the amplitude drops by a half, then the power or intensity drops by 1/4. The second problem states that the intensity in watts per meter squared of a laser beam used to burn away cancerous tissue when 90% is absorbed puts 500 joules of energy in a circular spot of 2 millimeters in diameter in 4 seconds. So, work is equal to power times time. Remember, power is work divided by time. And so this is equal to 90%, so 0.9 times the intensity times the area times the time. So this is, we have W over 0.9 times A times T is equal to I, which is equal to 500 divided by 0.9 times pi times 2 times 10 to the minus 3 squared, that's pi r squared, times 4 seconds. So the intensity is going to equal 1.11 times 10 to the 7th watts per meter squared.